Hello, we are Team 14, and here's our interim presentation for the analysis and redesign of a food processor. Our food processor is a device that processes food. Primary customer is domestic households, while the secondary customers are those such as kitchens with large volumes.
And then we have the exploded view of our product. The food processor includes the pusher, lead, cutter, fixer, cutter, and then connector, bowl, pin, speed control, switch, housing, and then the engine, cutter shaft, motor shaft, cutter pulley, motor pulley, belt, and the bases.
Next up, we have the functional analysis. As mentioned before, the main task is to process the food. Here are 3 basic functions and 4 supporting functions. Next up, we have the original fishbone diagram for the design. The drive is built on the bases by fixing the motor, then adding the motor shaft and motor pulley. The housing is then installed, after which the upper transmission is completed by inserting the cutter, pulley, and cutter shaft, finally closing the belt loop. Afterwards, the electrical parts are added, and the final assembly would be the bowl, which includes the bowl, connector, the pin, the cutter fixing, the lid, and the pusher.
Sequence restructures the work into vertical inside-out subassemblies that can run in parallel. The bases, the housing, the cutter, and the lid. The bases itself also contains 3 subassemblies running in parallel. When comparing through various criterion, assembly sequence 2 gets the upper hand of 13 points compared to the assembly sequence 1 with 10 points due to ease of locating parts, testing subassemblies, and parallel assembly. The function component mapping matrix consists of 9 functions, which are the nodes of the FAST diagram, and 17 parts, not including fasteners. You can see that there is a lot of overlap in the main functions, which is chop, slice, and grate. Around 10 parts serve the same function.
So after completing the FCMM, we charted out the bill of materials to estimate the unit cost of our food processor, along with trying to get the total quantity of individual parts in the processor. So after putting in the material, the manufacturing process, the assembly process, which in turn gave us the labor cost, material cost, the assembly cost, and the tooling cost, we estimated the total unit cost of the processor to be around $20. Over to Z.
On the cost chart, we can see a clear separation between cost and importance. Low cost, low importance parts such as screws are easy to manage, but high cost, high importance parts like bowl, lead, housing, and motor system drive both performance and expense. This highlights the key areas where redesign or material optimization could have the greatest impact. Next. In the functional differentiation table, we identify common functions: chopping, slicing, grating, disassembly, and locking. That define the core product family. Differentiating functions such as adjusting speed, connecting output more efficiently, and guiding insertion with a larger funnel allow us to customize the design. This makes the processor simple for household users while enhancing speed and workflow for professional kitchens. Next. Finally, the component commonality table separates stable platforms, like the motor and cutter systems, from flexible modules such as the bowl, lead, and speed control. Platforms ensure reliability and reduce complexity, while modules support variety and adaptation across different models. Together, they balance cost control with market differentiation. I move to Josh.
So after using all the product family design tools, this is the difference in assembly that we have come up with, which is an improved version. The key to note here is that the product differentiation comes in much later into the process, which means that lesser features work parallelly, which are much better for a product design overall.
All right, moving on. I'm not gonna cover the exploded view for the customer variant. In this case, the professional kitchen use. In this case, the pusher and lid are adjusted so that the opening where the food goes is bigger. And the cutter fixing, cutter and connector will remain unchanged. Here, we then need to adjust the parts are the bowl and the speed control. The bowl has a little slope inside and a spout that it flows out of so that the food can just be cut and immediately fall out into an extra bowl or something. And then we have this, instead of having a speed control dial, it's now just going to be a simple switch for the speed control from cut, slice, and grate, such that the user doesn't have to think too hard about it. And here, the engine, the general core motorized parts will remain the same. In terms of variants and interfaces, the bowl will be installed the same way using the pin connector for both variants. And similarly, the lid and pusher is installed the same way as well, just that the opening is different. And finally, the speed switch is installed in the same location. Even though it's works a little differently, it'll still be installed in more or less the same way. And that concludes our presentation. Thank you very much.